Everyone. We're just about to get started in the reading group, but my schedule's tight today, and Thunder sent me a question. I just want to see if I can really quickly figure it out, but Thunder, I might need to get back to you or ask someone else. Just confused, the third last line, you don't know what they're doing there. Well, yeah, what are they doing there? That's a good question. Rex, hey. Brian, hey. Obi, hey. I am about to hop into Discord and get the actual group started, but what is this? Oh, the binomial. Oh, I get it. Okay, yeah, I should have actually read. Binomial. There's a formula for binomial expansion, Thunder. This formula here, they're doing this applied to that is what's happening. And that's the quick answer. If I had more time today to actually show you, but the shorter answer is it's this formula here. They use, yeah, I think they probably did it, yeah, with the one in the entire rest of the series as the other thing, and then they arbitrarily cut off the series at the fourth power. Let me get a little pinned message here. Because I am going camping with friends this evening. Okay, awesome. Glad I was able to help Thunder. Elements of a 2 simplex. Okay, we're up in Discord. I see that Stooky's in here. Oh, that's not on the scene either. I'm sorry, Brian. Okay. Hey, Stooky. And then, Thomas, I'm not sure if you're going to be joining us today.
Oh, hello. I just got back at the right time.
Awesome. So I put the Excalibur link in the, voice chat. Or the text chat for the voice chat, yeah. Okay, there's Fembox. I know that Cook joined us last week. I don't know if he'll join us again today, but you can just go ahead and get started. Oh,
hey Don, hey Stooky.
Hey.
Hey,
Okay, so because it's the first day of a new chapter, I just kind of like to talk about the actual content. I guess I didn't have all that much to say on chapter 4. The main thing that was kind of weird or maybe interesting is how they explain conduction with that the example of a gas rather than through a copper wire like I would normally think of. But I think what they did in that section 4.4 made sense. It was just a little surprising that that's the example that they chose, but it's probably for a good reason.
yeah, I didn't get there, but...
Oh yeah, you can only do so much of it, right?
That is surprising, yeah.
Yeah.
Yeah, what was that? Was that the mean free path stuff from
yeah.
section 4.4?
It was.
Yeah.
I still don't quite feel like I understand what the Van de Graaff generator is doing. I might need to look up a different, an outside explanation of it, but
I think they said it was like a rubber belt, and it somehow got charged, and then it's sort of there's brushes on the top of it that pull the charge off. So you can manually crank charge from the bottom to the top somehow.
Oh, and I guess that's increasing the voltage at the top?
Yeah.
Oh, okay.
Oh, yes. Yes, that's also my understanding.
Okay.
Well, full disclosure, I didn't quite finish the chapter. I read most of it.
Oh, okay. And you said that you've studied circuits pretty recently outside this book too, so
yeah.
I'm gonna be making all these problems. You know, I'm just gonna look to you at every time.
Oh, great. Okay, no pressure, right?
Yeah. You know, when I was looking through the problems, I saw there was a 4-star one, and I saw just nodes connected with edges. I'm like, oh, this is graph theory. We should make Stuki do this one. But I looked it up, and I think it's like more of like a Markov chain. Is what it's more closely related to, or something like that.
Huh. Well,
But no, I haven't even read through a 4-star problem, much less tried one. But anyway, let's know if it has anything else to say about like the actual text. I can pull up a problem.
a little confused at gosh, let me just find the page number. 209 but it's 185. They're talking about this. It's just after this like curvy wire business. And that second paragraph starts in a region where the conductivity is constant, the charge density is 0. That feels like a strange statement to me.
Steady current. You know, not the first sentence. I don't see a constant.
In the second paragraph.
Oh, yeah, I'm sorry. In a region where the conductivity sigma is constant, the steady current condition divergence of J is 0. I think it's because any charge that's coming in at a rate must be coming out of at the same rate for whatever your little volume is. Or did you mean sorry, what?
I agree with that, but then we're led to this conclusion that the charge density is 0. That's the part that I'm like, I mean, it follows, right? But then now I'm confused about like what conductivity is doing in that case.
Oh, right. Okay, now I see the part that you're talking about, the second sentence. Density is 0.
Yeah.
Right, yeah, because we do know that divergence of E is proportional to charge density.
Right.
Yeah, why? There's no charge there. I didn't pick up on that.
Does that mean there's the same amount of positive and negative charge?
Could be that.
Be that.
And so they define charge density, I think, pretty early on in the chapter.
Oh, I think that's the other density.
Oh, current density.
Current
Yeah.
density, yeah.
Never mind. Yeah, and charge density is like it's a row from the previous chapters, but not resistivity row.
Yeah, we gotta watch our rows and sigmas now.
Yeah. Huh. Charge density. Yeah, I can't explain that. Steady current flow.
11. 11 is like Ohm's law? No.
Oh, I wonder,
Oh, yes.
could rho only be for static charges? Like, does it ignore the current density? Because they do go on to give that example with like there's a sudden wall of charge
Right.
in that conductor. in figure 4.6.
Mm-hmm.
So I wonder if charge density doesn't account, it only counts for static charge and not like conducting charge, I guess.
Oh, I mean, maybe, yeah.
Because I think divergence of E equals 0, or divergence of E equals minus rho over epsilon naught is only for electrostatics? Question mark. But that's my best shot.
Yeah, I read past there and I didn't even think about that, but it seems weird. The only thing I can think is that it must mean that if we're thinking of charge as having two signs, right, positive and negative, then if they were the same amounts of both kinds, maybe you could say, well, the charge density is 0.
Yeah.
Yeah, I guess that's the other possible explanation. Maybe this is a question we can hold on to if like we ever see Cook or Mary. Might be able to explain it.
So the opposite here is that if the charge density is non-zero, so if there's any charge, then that region is going to have the the conductivity is varying, which means that is constant with respect to time, presumably. So what I'm thinking about is I'm thinking about 4.11 in this context, right? The J is equal to sigma E.
Joe, you remember it as Joe.
Joe.
Only because I had a physics student named Joe once, so I don't know. It's stuck in my head since then.
Oh, that's great. And so I'm supposed to read that that when there's charge present, the ratio between the current and the field changes with respect to time? Question mark.
Sorry, I was just typing to Aller and hi Aller. What part was this?
Yeah, so I'm looking at Joe because I'm taking that as the definition of conductivity. And what this is saying is that if so what that sentence I'm confused about is saying is that if you have some charge, some net charge in the region, then the conductivity is not constant. So what the conductivity here being like the ratio, the constant of proportionality, what is the thing so that and this is why I'm confused about like time, constant with respect to time, constant with respect to the region of space, the point in the region.
Yeah.
Well, sigma is just.
So now I think.
Oh, Cook
now I
says
think
thinks he can explain. Sorry.
Oh yeah. Maybe Dr. Cook can hop on, but I was thinking current density is defined in terms of. I mean, it means something has to be moving, right? Because it's coulombs per second, right? Well, sorry, it's coulombs per second per square meter. So if there's no charge moving, then the current density would be 0. But then what does that tell us? It doesn't tell us.
Charge moving. The current is, yeah, agreed.
Does that resolve the question? I don't know. So if we got electrostatics again, then J would be 0, wouldn't it?
0. I'm happy with that, yeah.
Doesn't sigma only depend on the geometric properties? Like, why would it vary with time? So, sigma, like, depending on the shape, it could be like where it gets narrower or wider or a different material. That would change sigma? Or longer?
Okay.
Yeah,
I
it is,
think-
Cook. Sorry, go on.
They said we could
Okay.
consider it as a scalar quantity.
Wait, shit, where does it say that?
It's right at the right at the bottom of page 182. The same
182, okay.
the same
Yeah.
one with Joe on it.
Oh, sigma. Sorry, sigma can be. Okay, yes, yeah.
It's in the text chat for the reading group voice chat, Cook.
Yeah, it's possible to get to that chat without joining the without joining the call, but probably easier just to join the call first. You can keep yourself muted.
Like, that button right there. Oh, there. Or hop into, yeah, it's easier.
Where was the button? I missed the demo.
Oh.
I can't find.
Right there.
I don't know if that helps, but
Or you can, like, right click on it too.
Oh, open chat. Okay.
Yeah.
Okay, I see. Okay. All right. Oh wait, I gotta open this on my iPad. Sorry, 1 second.
good.
Okay. But yeah,
You already have problems copy pasted or copied at least.
I do, yeah.
Cool.
But yeah, I don't remember the book ever talking about the conductor as like a function of time, or like, I'm sorry, conductivity as a function of time, or like it would be a function of space, I guess, for if it like changes or something like that, or the temperature. Maybe the temperature would even change it, but Milk says conductivity is typically a function of frequency.
Yeah, I'm definitely willing to buy that when it says constant, it means spatially constant.
Okay. Um, so I'm not sure what else to like say about this. Okay. Excalibur board. Oh, hey, look at all this.
Oh no, I don't see it. It's near you. All right.
Steady current as, I think it's divergence, del.j equals 0. So j equals sigma e. So 0 equals... This is written by a PhD, you can tell because it's unreadable. The names of physics you can recommend that are readable by themselves. I probably wouldn't do this like per cell book that we've been doing. It's really tough, but I think Penn Center's been wanting to study physics as well, so you might be interested in seeing what he ends up doing. But I'm sure there'll be someone around who can recommend like maybe mechanics book or an easier E&M book. We're doing del dot sigma e is equal to del sigma dot e plus.
Can't argue with that.
Okay. The Riemann hypothesis, welcome in. I'll solve it on Saturday. I just won't tell you which Saturday. Oh, is this like a just... Or wait, what's happening from this step to this step? That's some dot product property?
Yeah, that looks like the product rule.
Okay. And then this del dot e turns into... I assume it's not 8 over 20.
Oh,
Oh, epsilon naught.
Q over epsilon naught. Is that Gauss's law?
Yeah.
Yeah.
Okay. Rho over epsilon naught. Okay. Gauss's law.
Oh, that's a row. Yes, that's a row. Sorry.
And so if this is also rho, is that we isolated rho? Okay.
Yeah.
So what is this last line? We found rho. Does this seem like it's turning into like Gauss's law? So if Nablus sigma is non-zero, the conductivity is spatially varying, then charge rho will develop. As claimed by Moore. Okay. Oh, I'm sorry, I see you put that earlier and I missed it. Okay, does that
That
maybe
okay.
address it?
This makes sense. Yeah. This is like this is a continuous version of that example that he throws out there. You know, it's like you could think about like a continuous charge distribution as being basically just like a whole bunch of walls, right? In that example.
Oh, okay, yeah.
And so that's okay. I'm happy. Thank you.
Yeah, thank you, Cook. The Riemann hypothesis asks what Gauss's law does. It's a little bit too long till I explain it in full, but Maybe it's the chapter 1 version is better to see. You basically can draw any surface you want around something making an electric field, and the flux through that surface must equal the charge enclosed divided by epsilon naught. And that probably doesn't make much sense to you. You haven't studied E and M, and trying to explain it from scratch would take longer than we have, but it's a cool thing. Okay, are we ready to maybe get into some problems then?
Yeah.
Yeah.
All right. Let's pull in number 1. It's a good place to start, unless you're a programmer. So,
Nice.
Van de Graaff current. In a Van de Graaff electrostatic generator, rubber is built 0.3 meters wide, travels at a velocity of 20 meters per second. The belt is given a surface charge at the lower roller, and the surface charge density being high enough to cause a field of 10 to the 6 volts per meter on each side of the belt. What is the current? Good, a drawing is like, good idea here. Surface charge density. I assume we're going to want something like I is equal to the integral of j dot dA. We're going to make some kind of like square on this belt for things to pass through. That's my assumption when I saw this problem, at least.
It's reasonable.
So if we put like just a square perpendicular to the belt or something like that. Or sorry if you're about to do something like that too.
No, I'm not.
Oh, that's what you're doing, yeah.
Oh, wait, hold on. Sorry. Not hold on, I just...
Hmm. So actually, if we have a positive electric field, I guess maybe we need to convert this field into a number of charge carriers. I wonder, can we go directly? Do we have to take that little diversion there? Oh, wait, J is equal to sigma E. No, never mind. We don't have conductivity.
Right.
Hmm.
Any is just a density with that.
Hmm. So
Potential difference.
I'm wondering, I'm not understanding how to bring the 10 to the 6 into it. 10 to the 6 volts per meter. I know a volt per meter is a Newton per coulomb. Does that help? Because we want coulombs, but what would we do with newtons?
we would take newtons and divide it by that, I guess, but dimensionally. I guess what I wonder, like, do we need to use like Gauss's law with a surface that's 0.3 wide and maybe like dx in length? Or
You
Yeah.
just want to turn that little square into a
oh
little
yeah,
box. Okay.
we can imagine that's a box. Dx, and then I guess the other dimensions can just be 0.3 each to make it a square. And the flux, I mean, it says a field on each side of the belt, which makes me think the flux through this box should be 0 because it's going directly out in both directions.
Oh, yeah. Well, when it's out in both directions, you add, right? So it's
Oh,
double.
true.
It's doubled.
Okay. So yeah, the flux through this thing then would be the surface area of the top and bottom of this box because it's going radially, or not radially, but perpendicularly outward. So, oops. We would have 10 to the 6 volts per meter times 2 times the area of just the top, let's say, which is 0.3. I don't know if we need to give a definite thing to this dx. I hope it'll cancel. Is equal to, I guess, surface charge density sigma with a minus sign over epsilon naught. And sigma is equal to charge in this thing divided by 0.3 dx. Because it's charge per area.
Sure.
And that seems like it does good things. Over 0.3 dx over epsilon naught. I'm going to move these red lines down just to give a little more room. Oh wait, they're not canceling. Oh no.
Oh, I see.
That's annoying. Is it because I use sigma rather than rho? Probably can't just arbitrarily make that a sigma because you feel like it, I bet.
Shouldn't this here be a Q instead of a sigma or a rho?
Oh, you're probably right. I was literally just showing Gauss's law. Oh, right, it's the Okay, if it's row, then you would integrate over the volume, but you could just do, yeah, Q. And there's no minus sign. After reading chapter 2, my memory of Gauss's law is all off, I guess. Oh shoot. Is something messing up with this Excalibur? Cause I wonder if. Oh, I did move your red lines down, Cook, and I wonder if there's a delay in when it showed up. Oops. Can we? Shouldn't be that hard to untangle. Sort of the spacing as I can. I might have already messed it up. I'm sorry. Your internet is not great right now. Oh, okay. Sorry, we happen to choose a similar area to write in. Maybe it was like that. Hmm. So should I have arbitrarily made it not DX? Or should I just made it like
Yeah,
0.1
I was
or
just about to
something?
say let's just let DX be 1 or something like
Or,
that, right?
yeah,
And
one's
then
probably easier. It's a little big, but who cares?
I like big Van de Graaff generators.
Okay, and this is a number that we can solve for. Dimensionally, this is, we have meters squared. Oh, I don't remember the meters of that epsilon naught. I don't want to figure it out. Actually, I mean, I have to look up the value of it anyway here. Okay, epsilon naught is Coulomb squared per Newton meter squared. I still don't feel like how the volts interact with that.
Well, let's change volts per meter to newtons per coulomb.
Oh, okay, that should do what we want it to then, and give us just a coulomb. 8 point. Minus 12 times 10 to the 6 times 2 times 0.3. Okay, so 5.3142 or... Oh no, this delay is crazy. Stuff is showing still a little bit like close. I'm just gonna come up here. Coulombs. Oh wow, Cook already got an answer here. Oh, using the field due to a plane? Wait, where would we go with our answer though? I want to see if we would, before I look to where it cooks. Um, so we are, this Q should somehow form our N?
Oh, that's the formula we needed, right? E equals sigma over 2 epsilon naught. I think that would have got us where we needed to get to.
Yeah. Maybe that's what I was thinking of with the sigma and the area canceling. I hear Texas has good connections. All right, let's just see what I guess Cook is doing. I is equal to sigma v. Is that times W or is that an X? I assume times or maybe cross product. That must be just be times. Where does that formula for current come from? I wonder if that's something that was actually in the book or if.
I guess it makes sense, right? It's coulombs per square meter times meters per second times meters. It's kind of just think it through.
Charge per
Surface
area.
charge, yeah, surface charge density times velocity of the belt times the width. I guess the W is the width of the belt.
Charge per area times transverse velocity is equal to transported charge per unit width. So then you multiply the width of the belt on both sides. Huh. Okay. It's fair enough. And so 2 times 20 times 0.3 times 10 to the 6 times epsilon naught. Wait, that's the same numbers that we did, right? Just for a different reason. How come I got coulombs? I guess I should have thought harder about the units.
We hadn't got around to bringing in 20 yet, I don't think.
Oh, that's why. So we take our 5.3 times 10 to the minus 6. Ooh. That's not going to be 0.106.
Milliamps, it might be.
Yeah, milliamp. Yeah.
Oh, okay. 20 milli would be 0.106. Oh, hey, okay, so it matches. Okay. So Cook's way is probably better, but we did do it a valid way too, I think.
We didn't have to use the formula with NE in it, right? We never used
No,
that.
I thought we would.
Charge times voltage per meter. No, times the velocity charge times.
I did still mess with my units.
Yeah, I think we'd solve for coulombs per meter, right? I mean,
Yeah,
that's
we
kind
must
of what
have.
we had. We had coulombs per meter
Right.
There we go.
because we'd thrown in one for the imaginary height of our slice of belt.
Okay. Well, that's a 1-star problem down, I guess. I'll post saying here's a better way to think about it. V times W equals the rate of area that the belt sweeps out per unit time.
Yeah,
Right.
square meters per second, right? That's exactly what I was thinking at the start. I just couldn't see how to bring the field into it.
Okay.
And it was
Yeah,
it was going back to think of but Don, you had the right idea with the little Gaussian pillbox or whatever. It's just we could have kind of used the shortcut formula that we knew for a plane, right? It was like a
Yeah.
non-conducting plane, and we were looking at both sides of it.
I think I derived that without realizing it. Sorry, I
Well, that's good.
differentiated that. No, okay. Okay, 50 minutes in. Let's see. There's one that I was. Okay, I'm skipping ahead a little bit in the list of things that I called out, but there was one that looked kind of cool. Number 7 here. We make a borderline. Bring it in. Oops. Oh my gosh. Okay. Wait, was it this one? Oh, yeah, there was a different one that I was actually thinking of instead, but this one was also, I thought might be cool. Since a resistor R, independent of the length of the page. Effective resistance between A and B. The numbers you encounter in your calculation. Oh yeah, that last sentence in part A is what kind of intrigued me about this one. So what's happening is we, I guess, have like each path increases the number of resistors by 1. So like directly from A to B, there's 1 resistor. Then if we travel here, and we'd encounter 2 resistors in series, right? And then here would be 3. We'd have to add these up with series versus in parallel, or like these would all be in parallel, I guess, but
Actually, we could start right at the top of this picture and collapse the top node, right? Collapse that one down, and then we just sort of come down and fold all these things in from the top down.
Right, I like that. So
yeah, series to parallel to series to parallel to series to parallel. Yeah, that's gonna work.
Not that. I should just copy paste that drawing. Why am I trying to remake it? There we go. So yeah, we can start with these up here, which I guess we could assign all of these. Well, they all have resistance R.
Yeah.
maybe I don't even need this copy of the drawing, but
So those two you circled will be 2R, right?
right.
And then we got 2R in parallel with 1R, so that's 2/3. You guys know the product over sum formula for resistors in parallel?
Yeah. I think we could equivalently draw a diagram
Oh yeah.
like that. How many?
Yeah,
One,
Don,
two,
you're
three,
right.
4, 5, 6.
Yeah, beautiful. Because this is a ladder, isn't it? I've seen this before.
This
They
problem's
call
gonna
this
be
a ladder
just
circuit?
like this. Oh yeah, it's like I think the a problem in the future is called like calls it a transducer or something, or it involves transducers. I don't quite remember. But yeah, this definitely seems like a thing that comes up. Um,
Yeah, beautiful.
so we could take. Excalibur doesn't want to. Why can't I select? There we go. Take all of that, and like the first step, we could deal with just that right side. And
2 to
say
3. Oh
that's
wait, is this
too hard.
is it Fibonacci? I bet you it's Fibonacci.
Oh, that could be a.
I'm feeling it.
And so how do we deal with? We have a resistor before in series with. Okay, so then we could boil those. Okay. We would take.
Oh.
These two resistors here and 1 over. Oh god, how does that fraction?
Wait a sec. Didn't you already cut off too many there?
Did I? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh. Yeah, I shouldn't have cut that one off. You're right. It needs to be. I did that one. Okay, and then. Oh, wait. Those two in parallel are the same as that one right there. Oh, yeah, that form of the fraction might be easier. Finite continued fraction. Oh, that might be why this is going to turn out to be Fibonacci or something. Familiar
I see.
thing. For 3R, which is 2/3 R. I feel like I saw someone write that before. Then we can continue this process iteratively. And I hope we see a pattern soon, so we have to do this like 6 more times, but oh wait, I cut it off too early. So that'll be 2/3 R plus R. So 5 over 3R. Okay, maybe instead of copying the entire diagram, we can.
Yeah, and then we get 5/3 over 8/3, so that's 5 to 8, right?
5/3 over 8/3. 5/3 R times R over. Oh, okay, yeah, I see the 5 to 8 now. So that means that will be 5 over 8r plus r. Fibonacci 5, 8, 13. Huh.
It doesn't just have to be rabbits. It can be resistors in series and parallel.
So it's, I guess physically it's a Fibonacci number divided by the previous Fibonacci number. So this one, I guess we could predict is 21 over 13r.
So we could probably prove this by induction, right? If we wanted to.
Probably.
Yeah. Where did that 5 go? Who cares? So what would the effective, so they do want like what the answer will be at the end result. Hey, Isai on YouTube? So once we include, I guess we just need to figure out how many more times this is happening. We'll get the next Fibonacci fraction from that resistor there, which is going to be 13 plus 21 is 34 over 21r. 55 over 34r. And then 89 over 55. I think is our final answer. It's my final answer.
Should those overlap? Like-
Should what?
If it's 34 over 21, should it be 34 in the denominator again?
Oh,
They advance.
I wasn't doing the pattern right, was I? We went from...
Yeah, I think they advanced twice.
Ugh, okay.
Yeah.
So we did 5/8, 13/8, and then 21 over 13. So we would keep the 13 denominator one more time to get 34 over 13?
No, so 34. Oh, yeah.
And then the denominator gets bumped up a Fibonacci. So we start working with the 21.
Yeah.
I hope. We might want to do it. Maybe we should do another calculation to actually verify that. So 20 over 13, I think we actually got that from somewhere. We would add 1 to it to get 34 over 13R, and then it's in parallel with another resistor R. So times R over 34 over 13R plus R. Wait, what?
Yeah, no.
That's going forward if it like 2 Fibonacci numbers are. Okay, the
Oh, yeah,
pattern.
seems. Yeah, that seems right.
Okay.
21.
Um,
Advances 1.
89 over 55 r times r over 89 over 55 r plus r. Let's just be 55. uh, why did we get 8 twice? Did I make a mistake?
So 8 should. Denominator should happen twice. Because once is. The first time it shows up is when you do the parallel calculation, and then you add a 1 in series.
So I think for this next one, I would be getting the next Fibonacci number rather than 55. Am I doing this too quickly? My 34 or 55 might not be right.
After that, that's 21. 21 over 13, so 4 over 13. And yeah, 55 over 34 perhaps? No,
Yeah,
still too fast, right?
I think that's right. Every time we do a parallel, every time we do resistors in parallel, we're kind of getting the next 2 successive terms in the Fibonacci sequence, the ratio of them. 1 over 1, then 3 over 2, and 8 over 5, and 21 over 13, then 55 over 34, right? That's the one you guys just got, I think.
Uh,
Or have I got them flipped? Maybe I got to flip them. Yeah.
Cook is saying the answer must be less than r. I assume because eventually you get to a situation with 2 parallel resistors at
yeah.
the very end.
Yeah, so everything I just said was flipped over. So it should have been 1 over 1 and then 2 over 3, right? That's what we got before, 2/3. And then 5/8, and then 13 over 21.
I feel like I need to do like, or at least for if I was doing this, I would just have to make a separate drawing for every single step here. I was trying to avoid that, but it's hard to do mental circuit math for me, I guess. Cook says, I think we're getting the same numbers. Okay, so some of Cook's intermediate R's were more than R though, like, or more than 1.
Right.
So just because we do have some of these that are more than 1, that's okay. Just the end result won't be. No, I just mean like 34 over 21. Like that thing. It's like this 13 over 8 isn't necessarily wrong then. Wait, 34 over 21. When we have 34 over 55. Right, so I had 34 over 55.
No, Dr. Cook, they're not all less than 1. They're all less than 1 when you after you've included the parallel. But when you include the one in series, you're adding 1 to it. And so that one is going to be more.
Oh, okay, we're talking about like different stages, okay. Of when we're breaking it down. Where 8 are. Then you would add 1 to it to get 13 over 8, which is in parallel with another. Okay, I think I messed up my green denominator. Oh wait, no, I'm just not tracking right. Never mind, it should be 13 over 8. That's okay. Then what happened to my red one? I think is flipped. Yeah. And that probably messed up the rest of the pattern. Okay, well, to get up to that stage, we're at 13 over 21 plus 1, which is 34 over 21 r. And then we include the one in parallel there. It's 34 over 21 over 55 over 21 r. 34 over 55. $89. What is... Excalibur turned my 8 into a sigma. Okay, and that'll be 89 over 55.
Okay, it's birthday time. I gotta head out, but
Birthday?
I will
Oh,
see you next week, if not sooner.
okay. I'll see you around. Thank you for being here.
See you, Stookie.
Um, 89 over 55 divided by 89 over 55 plus 1. Ugh. 89 plus 55. 144. Okay, we're nearly, or I'm nearly there. I just want to see if my answer is going to match Cook's at the end here. Were you listening at the Fibonacci numbers for 144? Okay, 233. Critical thinking is asking, what do you need to study to learn Calc 3? I don't want to get too deep into going off track here, but my favorite site is Paul's. What should you review? Just make sure you fundamentally like understand the concept of what a derivative and integral is. And other than that, I feel like it's kind of its own. You're taking the ideas from Calc 1 and Calc 2 and applying them in a new situation, is what I would say. So I just make sure your fundamentals for calculus are okay, and the rest will hopefully, it won't be anything that conceptually new, it'll just be applying the same things in 3 dimensions. Okay, 89 plus 155, or 144. Why did I say 155? From the Riemann hypothesis. Oh god. Then Alexi said 233 for the next Fibonacci number. Okay, and then just one last one. Which is the parallel for... That was going to be 233 over the next Fibonacci number, 377. I think that's what Cook got. Okay. I'll probably... I didn't expect it to be that arithmetic heavy, but...
Yeah, good thing they didn't give us, a dozen of those things to do.
I'm a little bit nervous because I also pulled one that is this like ladder circuit or whatever we called it, but it's infinitely long. So actually, this might be helpful. But we might save some work if we do try that one. Oh, the next part is infinitely many. Okay. It sure is giving you bad energy vibes. Oh, yeah. That lecture is kind of the worst. What is R effective in the limit of a very large number of triangles? You can assume that they spiral out of the page so they don't run into each other. I assume we want the golden ratio formula for like a Fibonacci number.
Yeah, I think that's it, right? I think that's it.
Like, yeah, we would divide n or n plus 1 by n or something.
Yeah, I remember that from number theory.
Oh wait, it should just be the yeah, the recurrence relation, I guess. I feel this is a stupid question, but like the next Fibonacci number is the golden ratio times the last one, right? That's not quite right.
If I remember rightly, it's like that you get if you consider the odd ones or the even ones, they sort of approach the golden ratio from above and below. If I'm remembering that right. So what we must be getting here must be 1 over the golden ratio, right? Because we need a number less than 1.
Oh, right. These should be, if it's approximation between two terms, yeah, this should just be 1 over the golden ratio. They're even involving a spiral in this just to be extra about it. Even though their picture doesn't even, like, it wouldn't spiral infinitely.
Well, they said they spiral out of the page so they don't run into each other. So it's like a spiral staircase, right? Coming out at us.
Oh, like that. Okay, yeah. Three-dimensionally out of the page. I feel pretty satisfied saying it's just like 1 over phi, where phi is the golden ratio.
Yeah. What's a way to do it? Can't we just, if it's going to approach a limit, can't we say that like it's a number where if you, what are we doing? We're adding 1 to it and then we're
1 over phi times r.
Yeah, we want a number where if we add 1 to it and then we multiply it by 1 and divide by 1 plus it, we get the same number back, right? There's a little formula we can set up and solve.
Oh, the continued fraction Fibonacci sequence. Is that what you're talking about? Isn't there continued
No,
fraction?
I'm just sort of saying it. If it's going to have a limit, then we can assume that whatever the limit is, if we add 1 to it,
Oh,
and then we multiply that answer by 1 over and divide it by 1 plus that answer, we should get back the same thing, right? So how does that work? Yeah, okay. So
Oh,
x
right.
equals
Yeah.
x plus 1 over x plus 1 times 1 over 1 plus x. Is this right? This doesn't feel right. I'm doing something wrong.
It might be more like that. My thing will just give you the polynomial or the quadratic for the golden ratio.
Yeah. No, you know what? They both work, don't they? I think maybe they both work. Let me try and do this and see what I get.
Okay.
So x times x plus 2 equals x plus 1. Yeah, so x squared plus x equals, so what am I getting?
Should we have x squared minus x? And plus 1?
Maybe,
No, wait,
maybe
I'm
my
sorry.
formula is,
You're
I think
right.
my formula is giving me the reciprocal, right? I think this is going to give me 1 over phi if I solve it. Let's see.
Put the EQ in top right in red. Oh god, Excalibur is getting really laggy for me. Might need to go
Yeah,
to a
my
new
computer
board.
doesn't like it.
Oh, okay, so this is for adding the next resistor in parallel. And this should give you the golden ratio. Maybe, probably, if we solved it for R infinity.
Yeah, you know, I was assuming R was 1, I guess, which I shouldn't have. I think we're getting the same answer.
Okay, let me export this and open up a new Excalibur, because this is getting a little ridiculous. How do I export? It's up here. There we go.
Yeah, 0.618. That sounds right.
Ugh. Okay, I had this exported. Let's I assume you can solve this equation that Dr. Cook set up for R sub infinity and get like 1 over phi times R.
Yeah.
That's the point. I just don't want to make Excalibur suffer any more than I am already. I'm gonna hit stop session. And then yeah, stop it. Ugh. Just let me have a fresh board Excalibur. Reset. I have this image downloaded, so I wonder if it'll be the same link. Oh, I could. Ooh. Put the link in chat here. It's a different link. Okay. Okay, maybe. There are some interesting ones later on, but I think we'll go back and go through the sequence again. Go to number 2 here. Actually, oh shoot, maybe this one involved the one that or that figure we were talking about with Stuki, but I forgot about they're being questioned with this one.
I actually did this one while I was reading the chapter, and it wasn't hard. So I don't know if I got it wrong, because when I saw 2 stars, I was like, uh-oh. But it seemed easy. I mean, I got it right away. So
Oh, okay.
I don't know if I did something simplifying that I wasn't meant to, but it worked out.
Well, charge at the junction of 2 materials is epsilon not I times 1 over sigma 2 minus 1 over sigma. This. I wonder if I'm getting too stuck in like chapter 1 and 2, but it almost seems like we use Gauss's law to get the charge enclosed here, but I wonder if it's a more convenient formula that we have.
Yeah, that was my approach. I just used Gauss's law.
Oh, okay. Oh wait, listen. Oh no, we have 2 different fields. Okay. So, okay, if you do it with Gauss's law, then I'll try that too. If that's our Gaussian surface, the flux through this thing is going to be, I guess E2 is positive flux. So we'll say E2 times A, because I assume the areas are irrelevant, minus E1 times A is equal to Q over epsilon naught. And do we need the definition of conductivity here? Well,
Yeah, Joe.
Joe. I missed the Joe thing. Like, why it's Joe, besides you were tutoring student named Joe?
It just looks like Joe. I mean, J equals sigma E. It kind of looks like JOE, so I don't know. That's
Oh,
why
I
thought
get
of
it. Okay.
Yeah.
Um, because I'm seeing like a Q over A here, and I'm trying really hard not to make it the other sigma. For surface charge density. The sigmas here are conductivity. Um, don't they give like a geometric formula for sigma, at least in like a certain case, like it's L over A. Oh, R is equal to L over A sigma. Huh. That's not what I want. J is I over A. Oh, is that what we need? J is sigma E. So, oh, okay, so maybe on this, well, I don't know if that last line that I wrote was necessary, but we could say that 1 over sigma 2 E, J, the J's are equal.
Yeah.
It's just the sigmas that aren't. Okay. Q over epsilon naught. And then J is I over A. Okay. What am I doing with the left side though? We don't want a Q there. Total, oh wait, no, we do want a Q there. The total amount of charge at the junction. So we just multiply the epsilon naught and we're done. Okay. Okay,
So
you're
that was
right.
what I did too. So do you think does that feel like it should have been a 2-star problem? It makes me think that maybe we cheated somehow. Maybe something we did was supposed to have a little bit more reasoning through it for some reason.
Yeah, the 1-star problem was way harder. I don't see what the error would be. Like, where else would an epsilon naught possibly come from? If not Gauss's law. I guess it's usually involved in the definition of like resistivity. I think, but we can check the answer on this because I definitely don't see what's wrong.
Yeah, if you want, they'll probably explain
What number
more
was
about
it?
it.
Okay, 2. They have a decently long answer for what took us a couple of lines. Okay, they do the same Gauss's law setup.
Hey, there's 106 milliamps for question 1 too, so we get that right.
Oh, right.
Point
Yeah.
0.106.
Actually, did they do it at... Okay, so yeah, they did the same approach as Cook. Yeah, critical it is. Okay, right. Q correctly equals 0. Okay, and if it... Oh, shoot, I wish I chose this one while Suki was here then, but...
Yeah, when we were talking about it earlier at the very start, I should have mentioned it because I thought, oh, that's the one I did. And it wasn't too hard.
Yeah. Sigma 1 approaches 0, which means conductivity. So the resistance is getting infinitely big. So Q equals negative infinity. So the book is about as short as ours, but they're doing some extra discussion in this last bit here.
Yeah.
Q approaches negative infinity. Region to create a non-zero J. I don't quite understand what's happening in this last bit where they let sigma 1 approach 0. Sigma 1 approaching 0 means the first region gets infinitely more resistive. And that implies that there's an infinitely large number of negative charges on that border part. Asserting the left region to create a non-zero J, so the large negative charge is necessary to avoid. To mostly cancel this huge field. Oh, okay.
Yeah, it kind of makes sense. If you have like infinite resistance, then to keep the current density flowing, you'd have to have an infinite negative charge on the other side of the wall, wouldn't you? I don't know.
Yeah. I think I get what you're saying.
Oh, another thing that I've meant to talk about before, because I remember when I was studying electronics, there was one textbook that I had that was called like the conventional current version. And when I was reading the introduction, it said they had two versions that they published, and one was conventional current and one was electron flow, right? Because I guess the current is defined in terms of the flow of positive charge, right? Like a coulomb is like positive things moving. An ampere is positive thing. If you got 1 ampere, if J is one in the x direction, that means you've got 1 coulomb per second moving to the right, but that's defined in terms of a positive charge, whereas really what's moving is electrons most of the time, right? That's always confused me too. It's another one of those things where there's a sign problem you got to watch for.
Hey, Arbucked. Yeah, so there's also that direction component where positive moving to the right, if you define it like that, is the same as negative moving to the left. And I wonder if they do some kind of directional monkey business like that to make it actually match the electrons that are doing the actual movement in most of the time with circuits. Unless you have a p-type semiconductor, or whatever the book was talking about in that section.
Yeah, and they were talking about that too, weren't they? Where they had like holes and they had electrons moving one way and the positively charged holes were moving the other way.
Yeah, I thought that was super interesting to read about, but pretty tough to like wrap my head around. But like the idea of just those chemical bonds flipping around that fast is kind of crazy.
Oh yeah, and then they were talking about electrons, and they said, well, we got to think of some quantum, mechanics, so that we can think of an electron not as really being a particle, but in sort of a wave form somehow.
Exactly,
Didn't
yeah.
they
And
say
it's like,
that?
yeah, and like the imperfections cause a scatter in the same way that like, or at least a similar way like a prism would scatter light waves, or it was something
Yeah.
like that. And I don't know, I kind of like dipping our toes just a tiny bit into quantum physics like that without having to actually
Yeah,
study it.
it's cool. It sounds really cool. The problem is when I read something like that, I feel like, well, I don't understand it. So
Me too.
yeah, it's kind of depressing not understanding it.
I don't
So
remember seeing
you're
anything.
going camping?
Oh yeah, I am, and I'm gonna leave like pretty soon after I stop the stream. But yeah, just gonna spend a night in a campsite not too far away with some friends.
Nice. Nice.
Yeah, I have
It's
time
been
for one
raining here
more.
today.
Oh really?
Yeah, we had a good storm a little while ago.
We,
I was
we
worried
don't
the
have
thunder would
rain
be
here.
too loud. Oh, really?
Oh yeah.
That's too bad.
No, I love the rain, but we actually had a pretty rainy winter last winter, which I liked a lot. But yeah, cook us more for Gabbro. True. Yeah.
You're
Block
more
stealing?
northern California, right?
Yeah.
Yeah, I've never really been north of like I've been to San Diego and Los Angeles, but I don't think I've ever been to like San Francisco.
Yeah, I mean it's pretty like overcast, uh, like super often, but actual rain we still don't have a ton of it.
Yeah, well, if you got time for one more, let's take a look.
Yeah.
Oh, Bloch's theorem.
Okay, this is like quantum mechanics stuff. Discover the theorem.
Yeah,
Electron wave functions
the
on
wave
effect
function.
periodic waves. Okay. I feel like it's a symmetry thing can be said about a lot of physics, and I still feel like I don't have my head wrapped around about how physicists use and think about symmetry. But okay.
Hmm.
What do I have? Okay. I mean, yeah, the one I have is even longer. This one might be a little. It looked a little weird, but it could be cool. I'll bring it in right below here. That was number 4. Oops. Trickster shells is fit from together for sensitivity row. It's a classic problem. Okay. You would always assign one to your students. Okay. You see, there's spherical shells not filled in. Resistance between the shells is essentially equal to rho over 4 pi r1, which looks suspiciously like electric potential. Well, I guess it's r1. Essentially infinite.
Surface area. Surface area
yeah.
of that sphere.
Okay. Got our classic resistance donut. Okay. the resistance between the shells is essentially... Now, I don't think I had a specific idea for how I would do this. How do they get the resistivity of a... or... We want the resistance, so we're given the resistivity. And so they did get the resistance due to a wire somewhere. V is equal to IR. They construct the resistance due to a wire by doing like, they mash together a whole bunch of equations. We're having a, I had to read it through a few times to actually follow what was happening with their substitutions. Um, see that Cook is going off and doing the problem, but I don't want to look like that closely at it yet. Hmm.
So,
Arrays R2 is essentially infinite.
some of these formulas might only apply to the case where we have a wire, though.
That's a good point. I was hoping we could like consider L as like the radial distance, I guess, and A as the surface area of a sphere.
Yeah.
But that is kind of an assumption, I guess.
And maybe do some kind of integral from R1 out to infinity. But what are we integrating?
Hmm. Do we necessarily need an... I don't know why we need an integral.
Yeah, I'm just brainstorming.
But a cool problem sum does not be helpful. Okay. I don't think so. It will be at least not yet, or not with anything that I see. Oh, you know, this chapter started to talk a little about the differential equations with circuits too. It did as an example problem the differential equation for an RC circuit. And I think I chose one that'll be another differential equation, but it'll be later on in these groups here. Oh, I think the books are the simpler one that's just first order. But yeah, I think I remember doing some second order circuit DPQs as part of one of my classes. The truncated cone example at the bottom of these notes. Okay, let's pull it up.
Can you guys hear me?
Yeah.
Yeah.
Okay. So at these lecture notes I sent you, that this example I think is kind of pedagogically useful of a truncated cone, calculating the resistance of that. And then I think if you understand this, the sphere one will make more sense maybe. So the idea is to use this formula that R equals rho L over A, but in an infinitesimal form. So you say like, so imagine you have some like little thickened coin where the thickness is dl and the transverse area is a, then the infinitesimal resistance dr would be rho times dx or dl over the area a. So that's the whole point. Is like you want to, if you have something where the geometry is varying in resistivity, you need to break it up into little coin cross sections and add those up. So in this truncated cone example, if you look at the purple, I'm using the infinitesimal version of that formula. dr resistance equals resistivity times L, which is dy in this case, over the area of that little coin ay. And by the coin, it's the green cross section above.
Oh, right. Oh, so that's where the
Okay,
integral
so
will come
then,
in. Okay. Or at
yeah,
some
the
point.
integral comes in when you adds up all these little drs, all these little coins. Okay, so that's the rough idea for this. You can actually calculate this, and you get a nice, cute little answer at the bottom there. But for here, for the sphere, the one way you want to think about it is imagine. Actually, wait, what's the question again? I'll make sure I don't say anything wrong.
So this would, okay, I think I got you then. So we can think of little spherical shells as we go out.
Yeah, can I see the question again?
It's on
Can you
screen.
pull it up on? Okay, I'm watching on Twitch. It's a little behind. Yeah, okay. So, yeah, here, yeah, exactly. Finbox had exactly right. So imagine breaking up into little shells where it's flowing like from the inner radius to the outer radius. So the area it sees is 4 pi r squared at that little distance r. And then if you
Yeah.
imagine thickening it, then the L in rho L over A, the L is dr.
dr.
So it becomes a 1 over r squared integral. The dr is on top because of L and rho L over A, and the r squared is on the bottom because of the A 4 pi r squared.
What are we actually integrating though, besides the surface area? Or are we just integrating the surface area?
We're integrating the infinitesimal resistance dr, or I mean capital R.
Oh,
there.
dr. Oh, okay, yeah.
So you're using the
And there's, like,
infinitesimal version of this. Infinitesimal version of that formula would be,
And L is dr, A is the surface area of the sphere. Okay.
right. So it's kind of confusing geometrically because it's not like any other example where the current's all flowing in one direction. Here it's flowing radially outward from the inner radius to the outer radius, equally over those two surface areas.
I wish I did an example like
I
that.
was, yeah,
Sorry,
that's
what?
good. That's good. So I was thinking that formula of the rho L over A, I was thinking it would only apply to, like a bar or something with constant cross section, but yeah, this makes sense.
Well, the thing is, Finvox is that's powerful enough to get any shape, because take that cross section, shrink it down to a little coin, and you can break up anything into little coins.
Yeah. Okay.
So the sphere, yeah, I guess you'd have to like flatten it out each stage and stack it on top, but geometrically it's the same thing.
Oh, that's really simple. Now that we see it.
Well, you guys should try the truncated cone without looking at it, because that's actually good. If you can do this, and
How are we naming things in that example? H, R1, and R2?
you try it. I'll put it on the whiteboard if I can get back to it. Unless you can put it for me. How do I do this? Oh, the chat. Yeah, I keep forgetting that. Yeah, just from that picture is probably fine. If you just copy and paste that in there.
Like, just get the top bit there, or did you want to get more?
Just the shape of it, the orange thing with the.
Okay. Hopefully this works once the delay comes through.
Yeah, so this is a good exercise. So I'm using Y here to parameterize the depth starting from the left.
Okay.
So
we want to
cross-section,
calculate the resistance from the left circle to the right circle. That's the question.
Yeah, and actually you don't even have to say that, because resistance doesn't matter, it can go either way. If you take a resistor and flip it around a circuit, it's still 1 ohm.
Yeah.
So left to right is the same as right to left for a resistor.
And
okay, so we could use the same little trick, right? Yeah.
We do need to get the radius, because that influences the area, but that's a linear in terms of with respect to Y.
It's kind of like a similar triangles thing, right? This is like the calculus problem where you're making a grain of sand by pouring sand on top, and you got to find out how quickly the pile's growing when given a certain height or whatever. If you know the rate of volume of sand being poured on. I know you can solve this one with similar triangles. So
to get the linear relationship.
Yeah, exactly. So we could even think of like taking this truncated cone and untruncate it, right? And just extend it all the way out to a point. And that'll give us the way to find the similar triangles. Like R1 to R2 would be H plus, would be capital H to little h or whatever. So it's a ratio of the ratio of the radii of the circles to the distance we've gone from the big circle.
Oh, I guess it'll
be like that. It's like the scaling factor we're looking for, I think. Something like that.
That should be Y. Well, no, I guess the bottom part should be Y. So it's H minus Y.
It's a linear relationship, so you need 2 points to define it. And here you can see from the picture, when Y is 0, R of 0 is big R1.
Yeah.
And R of H is big R2. So you know at 2 points it's a
Yeah.
line, so there's a lot of ways you calculate it.
Yeah.
Like that? Do I know my similar triangles? Sides should be in proportion.
Well, I don't know if I like this picture. H shouldn't go all the way to the tip. It should go to.
Is H
Oh,
the
right.
length of the side? Like the hypotenuse?
H is the whole. No, it's just the flat width.
Okay. Then I don't see what's wrong with the picture.
Maybe it's the same thing. Let's see.
Yeah, the little H belongs down here, doesn't it? This should be our little H.
Hey, Bubbles.
Based on the picture anyway, right?
H is a constant, though.
Okay, I think that's it.
Oh, I see my mistake. I assumed a pointed top. Oh, I get it. Yeah, okay. The cone is truncated.
Okay.
I didn't truncate
So
it.
that's the most annoying part of this whole problem. But the rest you guys should be able to do now.
Yeah, just
So
in
you
a
have the transverse
general
area.
form of line. Okay.
Yeah.
And so dy is our L, and A is pi
Pi
r
r
of y squared.
Yeah.
Integral R2.
You know, a good problem after this you could do is the resistance. Take a ball of resistive material rho and calculate the resistance between two antipodal points on the sphere, maybe north and south pole if you like. You could do that just by chopping it up into flat disks. Using this formula too. Maybe some trigonometry, but it'd be kind of cool. Like if you just had like you could use that to calculate the resistance of a baseball roughly. Putting the leads on the antipodal points.
Yeah.
This is an annoying integral. I guess we could do a U sub to get rid of the constants.
Yeah. And the U sub actually has a nice physical interpretation after you see it. I think it corresponds to.
Oh, does it flatten it or something? Or make it a.
Yeah, I think it brings it to the point that you wanted, I think. Haven't done this in a while. So this is an example I made for my lectures. Because then after you got the formula for this, there's a nice limit we can take. When R2 goes to 0, when it is a point, as an interesting limit.
I don't want to figure out what the bounds are supposed to be after this U sub.
We did a problem like this in chapter 1, I remember. Some kind of
really?
truncated cone. Yeah, remember that?
Maybe like the field due to 1 or something?
Yeah. Yep.
I guess we're ready to integrate, aren't we?
Although,
I was gonna unsub and then put the bounds back in, if that's what you.
Oh, okay.
You were.
Okay,
Yeah.
I'm just following you. That's all.
Because I didn't want to deal with doing that algebra.
I have the answer on those notes if you want to check.
Oh, yeah, probably a better idea. I
Well, I
have to
don't want
go
to
soon.
rob the fun of the prom for you. Just, yeah, when you're ready to check. How much time do you got?
Oh, I mean, the clock just struck 3, so in my time zone. So I think I should head out. But let's put the answer. So I think we set up the interval right. Which is the important part.
We need that R2 minus R1 over H factor somewhere.
We do need that. You're right.
Oh, so you can. I did the calculation here too.
Yeah, I was just looking at the right answer.
Oh, you set it up right. Yeah, it's the same setup.
Yeah, and that's what I should have had on the outside.
Oh, so it's 0 to H over Y, and then it becomes R1 to R2 when you make the use
Oh, if you actually do change the bounds, it's really clean. Okay.
And so it's two things to notice about the final formula when you're ready for it at the bottom there.
I'm ready.
Product of the two radii.
That is weird.
Well, there's one way you could have seen it is that just to Finvox's point, if I flip this truncated cone around left to right, it should be the same because the resistor doesn't know left right versus right left. So the formula had to be invariant between switching R1 and R2, and this formula is because switching
Symmetry.
R1 and R2 is like flipping. Yeah, exactly, flipping resistor left to right. So that's a pretty neat fact.
Hmm.
And then another cool thing about this is if you take either one of the radii to 0, so you take it down to a perfect point, then it doesn't matter how small h is. It doesn't matter how short this thing is. If there's a point anywhere, you get infinite resistance. And it's just because that area can never go negative or can never go 0. It'll always create an infinite resistance. Because it's like, what's the resistance through my pipes when the faucet's closed? If it's blocked off, it's infinite resistance.
Yeah.
And then
Yeah,
a
okay.
point is blocking it off. No current can go.
And if R1 equals R2, you just have a wire.
Yeah, that's another good limit too. Did I have it there? Yeah, nice.
Yeah.
Yeah.
Oh, I see. Pi r squared. Yeah. Okay, I get it. Yeah. Right.
So when I'm teaching E&M, usually my students, they didn't have a good mechanics background. So I try to create these examples where they can test limits. And this is a good one because it has all these different limits to it.
Yeah.
Yeah, my mechanics are terrible, so it's helpful.
Yeah, so this is actually, I think I gave my whole lecture notes to Finvox. Maybe he passed it on, or maybe I put it in the Discord. I can't remember.
Okay.
So there might be some more nice examples there if you're curious. I know you probably have to read it first to help.
You did send it to me. Is it in Discord? Is that where it is?
I definitely DM'd it to you a while ago. I don't know if I put it in the chat myself. Oh, because it might have like personal details on it. I think I just DM'd it to you. I asked you to pass it on to Don, but it may have nothing personal in it. I just haven't checked.
Yeah. No, I got it here. Here it is.
Yeah, feel free to
23 FEM. That's it, right? FEM. Yeah.
Yeah. 2023 fall E&M.
Okay. I do gotta wrap things up and get out of here though.
Yeah, okay, this was fun, Don. Finvox, as always.
Yeah, good problems today.
Yeah.
Right.
Thank you both for being here and for the bonus problem, Cook.
Yeah, I like that truncated cone. That was a good one.
Yeah, I thought you guys would like that.
Yeah. I'll see you two around. Thanks for coming by.
All right, Don. Have fun camping. Have a good trip.
I will. Thank you. Have a good Saturday.
Thanks.
Okay. So let's cut the YouTube stream off here.